In this video, I'm going to talk about Newton's laws and collisions. This is part of the IB Physics Syllabus. Please read the success criteria for the following things I plan to cover in today's video. Okay, let's start with the review of Newton's three laws. I'm sure you know them already. So the first one, if the forces on an object are balanced, i.e. there's no net force, it will travel with a constant velocity. Now sometimes people say for this one, an object at rest stays at rest, and an object in motion stays in motion. But there's really no distinct difference between those. If you're at rest, you do have a constant velocity. It just happens to be zero. So I also like making sure I say velocity, and you can see it's underlined. It's not just any speed, because if you change direction, that must be a force. So it has to be traveling at a constant speed in a straight line. Number 2, the net force acting on an object is proportional to the rate of change of momentum. Now, in the past, you might have been told about this other equation. And you know, your teachers didn't lie to you. This can reduce down to F equals ma, but only in a very specific case. So let me just put this out here. So force is the change in momentum per time, because that's what it means when we say the rate of change. So if I do that, well, momentum, that's mass times velocity. And if I have mass, and let's say I'm changing my velocity over time, well, now I've got right here, that is my acceleration. But look carefully. I don't actually have to have a changing velocity. I could have been having a changing mass. And if that was the case, then what my equation would have looked like was the change in mass times the single velocity over time. Examples of that would be, let's say you're driving a water truck and there's a hole in the bottom and it's constantly dripping out water, changing the mass. Or conversely, say you're a train and you're being filled up with, sand in the bed as it's moving by. So we could have a changing mass per time. So Newton's second law, as force of the rate of change of momentum, is a more generalized application rather than F equals ma. One last thing I like to point out is I do usually write the word net when I write all of these equations. And the reason for that is I don't want you to think it's just any equation, and if there's multiple forces acting on an object, we need the unbalanced or the overall or the net force in order to use this equation. And finally, Newton's third law. If object A exerts a force on object B will exert a force back on object A that's equal in magnitude, size, and opposite in direction. Notice that Newton's third law refers to two separate objects, where Newton's first and second law are talking about a single object. That means anytime you think about Newton's third law, you need to be thinking about a pair of objects. Which two objects are involved in the reaction? Okay, so let's apply this to collisions. Here you can see I've got two balls, a green one and a yellow one, mass 1 and mass 2, and I've got u1, u2. Remember, u means the initial velocity, and then I've got them when they collide, and then after, and notice I'm going to call it v1 and v2 for final velocities. Now, they don't have to have the same velocities. In fact, they better have different initial velocities or they're not going to even collide together. So when they come together, we know that they're changing their velocity. And the only way to change a velocity is if you had an unbalanced force. So that's Newton's first law we're using right there. Since there's a change in velocity of each ball, they must have experienced a net force. The net force on M will be to the left because it's going to slow down. So it's going to be accelerating in the opposite direction of its motion. And U2, number 2, will be having a force to the right because it's going to speed up. Now, as for the size of that force, we can use Newton's second law. Here's the general version again. Remember the change momentum over time. And what do I have? I've got the final velocity minus the initial velocity. And that's just going to calculate our change in momentum. I've got the momentum at the end, the mass times its final velocity, minus the momentum at the beginning, m times the initial velocity. And I've got that for both of our balls. So let's now apply Newton's third law to this same situation. It said that the forces are going to be equal in magnitude. F1 will equal F2, but opposite in direction. So that's why I've got this negative sign here. So now from the last page, or the last slide, I had F1 was m1v1 minus m1u1 all over t, and I'm going to do the same for F2. So the first thing I need to do is I'm going to cancel out all of those time, because it's impossible for them to be in contact for a different amount of time. If m1 hits m2 and it takes 0.2 of a second, then both of them are in contact for 0.2 seconds. And then the next thing I've done here is I have expanded through this negative sign, and I have put through, so this would be negative m2, and then this would be a plus m2u2. What else did I do? I moved all my u's to one side and all my v's to one side, and I get this final equation. Pause now and make sure you can get that equation on your own. So let's look in a little bit more detail. What do I actually have? On the left side here, I have m1 u1 and m2 u2. This is just the momentum before the collision. And on the right side, m1 v1 plus m2 v2, that's the total momentum after. Don't forget, v stands for velocity, not speed, so it's a vector. And in this case, I'm going to say positive is to the right. One last thing I want to point out here is we haven't talked about what kind of collision this was. We've just done this in general. So what this is meaning is that momentum should always be conserved. Let's be a little bit more formal. The law of conservation of momentum. For an isolated system, the total momentum before a collision will equal the total momentum after the collision. So let me point out what this means by an isolated system. It means there's no external forces present. So when I have the two balls hitting each other, I don't have something on the outside, like let's say it's a metal ball and I have a magnetic field and that's somehow influencing its motion. Okay, everything that's going to have, I've got internal forces between A and B. Now, one other kind of cool thing is it's not just collisions. This will work for explosions as well. And I usually say there are two things in my class that I will panic if you ever tell me are not conserved. One is the conservation of energy, and the other is the conservation of momentum. Now, there are a couple different types of collisions. You can see here my title, Elastic and Inelastic Collisions. In an elastic collision, not only is momentum conserved, but so is kinetic energy. With inelastic collisions, momentum will have to be conserved always or I panic, but the kinetic energy is not. So let's take a look here. I have this Newton's cradle. So if I have one ball here and it hits, do you know what happens? One ball pops off. If I have two balls here and they hit, guess what? Two pop off. And the reason for this is not just the conservation of momentum, but also because of conservation of kinetic energy. And you could work yourself through this. If it wasn't being conserved, then how do I know how many balls would bounce off? If I had one really fast one, why don't I get two slow ones moving off? Would that still not matter? Would I still not get the conservation of kinetic energy? And the answer is no, because that v squared. So another example of elastic collisions would be billiard balls. Those are the two most common. In those cases, almost all of the kinetic energy here will go into the kinetic energy after. But we do have some other examples where that doesn't take place. If you take a look here, my two cars crashing. Some of that kinetic energy is going to go into what we call internal energy, partly due to thermal energy. Remember, not heat. Heat is when energy goes from a hot to cold object. But this would be thermal energy, some into sound and some into the actual internal energy of deforming that shape. Another example here, and I'll give you an example later, is a bullet and it's being fired into a block and it stays inside. Anytime two objects stick together after the collision, it is a total inelastic collision, and you know for sure kinetic energy is not conserved. Momentum is, not kinetic energy. Okay, so here we have a bullet and it's going to hit a block that's hanging from a rope. And you can see it's going to swing about here and it can swing up to a certain height. And this will be the maximum height it can reach. The question asks, in order to calculate the speed at which the bullet struck the block, what should be applied to the situation? What will I need to know? So Newton's first and second laws, well, do we have force being applied? Well, I don't think I'm actually going to need to use those. Conservation of energy only? Conservation of momentum only? Or both? Well, let's just check that out. When it reaches the top, it only has gravitational potential energy, mgh. And in this case, that m is going to be the mass of the bullet and the mass of the block. Where did all of that energy come from? It came from the kinetic energy that we had down here. And in this case, the amount of kinetic energy as it starts to swing will be 1/2 m, which is going to be m plus m, and whatever speed it has after the collision before it goes up. And then if I think even back before that, I had the mass of the bullet and whatever speed it was traveling. My block had no momentum, but then afterwards they've stuck together, so my total mass is little m plus big M times the same speed that I'm looking for down here. Let me make this a little different. All right, so if I want to know this speed right here, then I need to be able to know how fast it was going after, which means I'm going to have to use my conservation of energy because these two pieces will equal each other. So in this case, I'm actually going to need to use both conservation of energy and then the conservation of momentum. Okay, a body of mass m moving at velocity v collides with a stationary body. Let's draw that out. Moving at v, hits a stationary body, and then afterwards they're going to stick together. So now our mass is 2m. Which row describes the momentum and kinetic energy of the two bodies after the collision? Well, we know that momentum has to be conserved. So if I have m times v for momentum beforehand, afterwards 2m times v prime, with this prime being the speed afterwards, are going to have to be the same. So we know the momentum is going to still be m times v. Now let me just rearrange that. So v prime is going to equal 1/2 of v. So if I look at the kinetic energy afterwards, I'm going to have 1/2 m, which is going to be 2m, times v prime squared. So that's going to give me just m times v over 2 squared. Gives me 1/4 mv squared. And my answer is A. Notice because this is an inelastic collision, I can't just assume that the kinetic energy is conserved, like I did with momentum. A body initially at rest explodes into two masses. So before, here we go, and afterwards I get m1, let's put it going that direction, and m2 going this direction. They move apart with v1 and v2. Now notice it does say speeds, so we don't have to worry about directions here. Total momentum before is 0. Total momentum after would be m1 v1, m2 v2. And I know they're in opposite directions, so these two things are going to have to actually equal if I put in the fact that they are in opposite directions. So if I want to move this around to v1 over v2, that's going to give me m2 over m1? Answer is B. Okay, example 4. We have a metal block traveling in a straight line at 10 meters per second on a smooth surface. So what they're trying to say there is we don't have any external forces, so this is an isolated system, and we will have momentum being conserved. One other thing to note, metal blocks typically will have kinetic energy being conserved, but we're not going to make that assumption. So we're given the masses of the two blocks, and we're told that they're going to collide, and afterwards you can see they don't stick together. We do know that block A is moving at 5 meters per second, and we need to find out what block B will be moving at. Every time we have a collision equation, we want to start the same way. We want to write down total momentum before equals total momentum after. We want to make it very clear to the examiner that we understand we're using the conservation momentum, and we're not just randomly writing some equations or values written down on our page. So let's go through. And what I've done here is I've written in the total momentum of A before, because it was moving at 10 meters per second, mass times velocity. The other one's at rest, so that's 0. And here we are after, and I've written V prime after, just to denote it's not the same as the initial velocity. Now I'm just going to do some algebra. I'm going to put all my numbers on one side, and I end up with 14 meters per second. I'm just going to write that up here. Notice it's positive, which means it's going to be written to the right, or moving to the right. In the collision now, it says that they're in contact for 0.05 seconds. Calculate the average force that's acting on our block. All right, so I'm going to use Newton's second law in momentum form here, because we have the time it takes for them in contact. If I put in some values, I know that my change in momentum, and I pick up my calculator and I get 420 newtons. Notice that if you put in the values for A, you should get the same value, right? Newton's third law, they're just going to be equal in magnitude and opposite in direction. Part C. After collision, the total kinetic energy of the two blocks is less than it was before. Suggest one reason for this. So where'd the energy go? It doesn't disappear. So one thing you could suggest would be it goes into thermal energy and into changing the shape. Small amounts would go into sound. Remember, you only want one answer for this. If you have one correct one and one incorrect, then you will get 0 marks. This is not, I list as many as I want to and hope the examiner reads through and chooses the one correct one and ignores all the wrong ones. It used to be they marked the first one always, but things have changed. So if the first one was right and the second one is wrong, you will get 0 marks, not 1. So please read through the success criteria one more time. I hope after this video you can say yes, I can to all of these statements.